Alrighty, so today what we're looking at, guys, is our last exercise on transformations. So we are looking at graphing combined transformations today. So yes, we do have a bit of graphing to do, sorry. So we can find, just listening, thank you. We can find points and sketch the graphs of functions that are changed by a combination of transformations. So our translations are our easiest transformations to use since they shift the graph while keeping it the same size. So when sketching transformed graphs, there are two main approaches we can take. We can apply one transformation at a time, sketching multiple intermediate graphs before the final function, or we can consider the effect of all transformations on our point xy, on our original graph, our parent curve, therefore coming up with the coordinates of the image of P. After plotting a few key points, the rest of the transform function can then be sketched. So we're probably going to do it the second way because that is probably a little bit easier rather than sketching lots of little functions. So what we have to do for the first one is sketch the graph of y equals x minus 2 all squared minus 5. Who can tell me what my parent function is here? Y equals x squared is my parent function. Okay, so what we have is we have y equals x minus 2 all squared minus 5. What are my transformations that have happened to y equals x squared? We have our horizontal translations. We're just going to do it as HT. And what have we done? We've moved 2 units to the right. And then we have our vertical translation as well, 5 units down. So what we have is if we have the point x, y, what happens in order to get our transformed point, okay, is, or our image point, so we're going to use an I for our image point, is it's going to be x plus 2, y minus 5. So we were doing this a little bit yesterday and last lesson as well, because what we're doing is if we're moving a point to the right, we're adding 2. If we're moving something down, we're minusing 5. So that's what we're going to do to all of our key points. So for our key points on our graph y equals x squared, we have the key point of minus 2, 4. We have the point minus 1, 1. We have the point 0, 0, 1, 1, and 2, 4. They're our key points on our parent function y equals x squared. So to get to our transformed function, what we're going to have is we're going to have minus 2 plus 2, 4 minus 5. And so that equals the point 0 minus 1. Does that make sense so far? Then our next point will have minus 1 plus 2, 1 minus 5. So that is the point 1 minus 4. Then our next point is 0 plus 2, 0 minus 5, so that is just the point 2 minus 5. Then we have 1 plus 2, which is 1 minus 5. So we'll have 3 minus 4. And then finally, we have the point 2 plus 2, 4 minus 5, gets us the point 4 minus 1. So we get those points on our graph. Now, what we need to do is label our axes. Sorry, I should have given you one already labelled. Okay, so just going every second point across. then we can plot our blue points, so our transformed points. So our first transformed point is 0 minus 1. Then we have 1 minus 4. Good morning, Sophie. Then we have 2 minus 5. Then we have 3 minus 4. And then we have 4 minus 1. From here, we could work out some other key points. So at 5, it's going to be up at 4. That's just by putting it into my calculator. Okay, or at minus 1, it's also up at 4. There is also nothing stopping you from just putting it into your calculator as well with your key points in order to sketch. Okay, but the whole purpose of this is getting used to what the transformations are and making it a little bit easier for us. Okay, so that is our curve. Anyone got any questions there? What we could have done while you're copying that down is we could have sketched our original function and then moved it around as well. So if we had have done it that way, we would have sketched our original curve. We would have then moved it 2 places to the right. So then it would become here. And then we would have moved it all down by 1 as well. Okay, so the pink graph, so the green graph is our y equals x squared. You don't have to draw that on that. I'm just trying to show you. And our pink graph is y equals x minus 2 all squared as well. Does that make sense? But you don't need to draw any of that on there. Okay, that's just me showing you what you can do as well. So you can draw the green graph first, move it across to the pink graph, and then down to the blue graph if you'd like, or you can just do it the point way. Okay, part 2 of this question is asking us to use the graph to solve the inequality. So when we're being asked to solve the inequality, what we're being asked to do is we're being asked to solve the inequality x minus 2 all squared minus 5 is greater than 4. So what we want to do is we've already sketched the graph. So above we have sketched the graph of y equals x minus 2 all squared minus 5. Now what we want to do is we want to sketch the line y equals 4. So when we draw our straight line of y equals 4, I knew that would happen. So when we draw our straight line of y equals 4, what we want is we want our graph to intersect at 2 points. So we have that it intersects here and it also intersects here. So this point here is the point minus 1, 4, and our other point is the point 5, 4. So if we're writing an inequality, what we want is we want where is the graph greater than 4. Okay, so where is our function greater than 4? So we want it, where is our function above the line? So above the line, it's these bits here, isn't it? Does everyone agree? So because it's above the line, that means our solution is going to be that x is less than -1 and x is greater than 5. So like when we were doing we've done this earlier with our quadratic inequalities and graphing them and seeing where it's greater than 0, less than 0. Same thing, but now we just have other lines involved as well. Does anyone have any questions about that? Turn the page when you're ready. Okay. So our next one here, we're going to do it in the all the different ways, okay? So we're going to go in an order and we're going to get our final function. So what we have is the graph of f of x shown is reflected in the y-axis. It's dilated vertically with a scale factor of 2 and it's translated 1 unit up, and then we're going to sketch the transformed function. So we're going to do it step by step this time instead of doing it via the point. So the first thing that we're told about is that it's reflected in the y-axis. If it's reflected in the y-axis, it is horizontal dilation. And so what we have on our original graph is we have some key points here. We have the point -2, 3. We have the point 4, 3. And we have the point 1, -1. So when we are reflecting it in the y-axis, what we want to do is we want to multiply the x values by a equals -1. So what that means is all of our x values are going to flip. So the point -2, 3 is going to become the point 2, 3. Our point 4, 3 is going to become -4, 3. And our point 1, -1 is going to become the point -1, -1. Okay, and then we just want to draw our curve between them. We're going to put those points on as well. Is that making sense to everybody so far? So we've just applied our horizontal dilation. The next thing it's telling us to do is that our graph of fx is dilated vertically with a scale factor of 2. So that's our vertical dilation, and we have our scale factor equals 2. So what that means is that k equals 2. Oops. So we are going to multiply our y values, because we're talking about vertical. We're going to multiply our y values by 2. So multiply y values by k equals 2. So we're talking about our y values on our horizontal dilation curve, because we're going to attack each curve as we go. So the point -4, 3 is going to become -4, 6. The point -1, -1 is going to become -1, -2. And our point 2, 3 is going to become the point 2, 6. And from there, we can sketch our curve. Okay, the last transformation that we have is that we have to translate 1 unit up. So if we're translating 1 unit up, we're doing a vertical translation. So when we do our vertical translation, what that means is we are going to add 1, or add c equals 1 to the y values. So those y values that we just had in our vertical dilation, we're now going to add 1. So the point -4, 6 becomes the point -4, 7. We then have the point -1, -2 becomes -1, -1. So that was -4, 7, -1, -1. And then our point 2, 6 becomes the point 2, 7. And we sketch our function, and then what we do is we can then just put our final function. It is that final function with our vertical translation. Okay, so we're just going to copy that function across. So -4, 7, -1, -1, 2, 7. That is our final function with the points on it. 2, 7. And this function is in the form of y equals 2 lots of negative 1 of our x plus 1 for our c value. Okay, because remember, when we're talking about our transformed function, it's y equals k, f of, oh, I forgot the f. There is meant to be an f in there. F of, if you forgot the f, don't worry, minus 1, which is our a value, x, plus 1, okay? Because we don't know what that function is. We just started with our f of x. So in that example, we took one transformation at a time, okay? In the next one that we're going to do, like the first one, we're going to take the transformations together in the correct order and plot images of key points on the original parent curve. So like what we did on the first one. So flip the page for me. So you can choose which method you prefer to do for this as well, okay? So we have the function y equals fx is sketched below with stationary turning points as shown. We're going to describe the transformations if f of x is transformed to y equals 3 f of x plus 1 minus 2. So the one thing that we need to remember is that we are dealing with y equals k f of a of x plus b plus c. Okay, so our k value is going to be 3. Our a value, well, there's no a there. So a is just going to be 1. Our b value is plus 1 and our c value is minus 2. All right, and we're seeing how they're going to change the coordinates of the parent function. So we want to do our describe the transformations in order. Okay, so our first transformation that we look at is our horizontal dilation. Because remember, we go in alphabetical order. So horizontal dilation, we just have that a equals 1. Okay, so there is just an imaginary 1 there. So there is technically no horizontal dilation. The next thing we look at is our horizontal translation. Don't know why my pen keeps running fat. Okay, so our horizontal translation is b equals 1. What that is doing is moving 1 unit to the left. Because it's positive, it goes to the left. So if we look at our coordinates x, y, what that does, our horizontal translation, it is going to change it. So we'll have x minus 1, because we're moving to the left, we have to minus 1, the opposite of what b is. And then we'll have our y still, because we haven't affected our y just yet. The next transformation that we have is our vertical dilation. So our vertical dilation is k, and it equals 3. So that means we have a scale factor of 3 is how we describe it. And so when we have a scale factor of 3, so we start with the coordinate that we ended with. So we start with x minus 1, y. What we have to do is multiply our y value by 3 when we have a vertical dilation. And then lastly, we have a vertical translation. And with our vertical translation, it's a c equals negative 2. So that means that we are moving it 2 units down. So we start with the coordinate that we ended with. So we start with x minus 1, 3y, and that is going to become, once we apply our vertical translation, it becomes x minus 1, 3y minus 2. Does that make sense? I'll give you a second to catch up if you're still writing. Okay, so part B, what we want to do is for the coordinates of find the coordinates of the image of each stationary point when the function is transformed. So our stationary points are our turning points of our curve. So our turning points are our maximum point, so where that minus 2, 5 is, and our minimum point where 1 minus 9 is. So what we're going to do is for our stationary point of minus 2, 5, we are going to input this into our x minus 1, 3y minus 2. So we are going to sub x equals minus 2, y equals 5 into our x minus 1, 3y minus 2. So what we therefore get is we'll get our x value is minus 2, whoopsies. So we'll get minus 2 minus 1, 3 lots of 5 minus 2, and that becomes the point negative 3, 13. Does that make sense? It's sort of what we've done the last 2 lessons. Would have been helpful for those, wouldn't it? All right, the last one is for our other point. So our other stationary point, which was 1 minus 9, I think. Is that correct? Yeah. Without me scrolling up. So what we want to do is we want to sub x equals 1, y equals minus 9 into that x minus 1, 3y minus 2. So what we will have is 1 minus 1, 3 lots of negative 9 minus 2. That becomes 0 minus 29. So from here, now that we have those points, we can then sketch the transformed graph. So it is going to look like what it does up above, okay, except we are going to have our point is now at minus 3, 13 and at 0, 29. So what we're going to do is we're going to only draw a very, we're not even going to do anything on our axes. We're just going to draw it and then we're going to put our information on our axes. So by drawing it, we're going to start up here, go up. We want to make sure that we bottom out through our y-axis because our stationary point has moved to bottom out between 0 minus 29 and then go back up again. Okay, we're going to label that point 0 minus 29 and label this point up here as minus 3, 13. Okay, we're not going to put anything on our axes. We're just putting those key points because we don't care where our x-intercepts are. We just care what's happening with those key points. And then we're just going to write our y equals 3f of x plus 1 minus 2 on our graph. Do we have another page? Yes, we do have another page. Damn it. We're nearly there. Okay, this one's nice and easy. It's Noah's favourite for the next one. So turn the page when you're ready. You will need a ruler for the next one too, because it's an absolute value function. You feel like that? Yeah. All right, are we ready to go through the next one? So, what we want to do is we want to describe the transformations if y equals the absolute value of x is transformed to y equals the absolute value of x on 2. plus 3, and then the image point xy on our parent function. Then we're going to sketch. So what we have is this is in the form of y equals k, the absolute value of a lots of x plus b, absolute value plus c. So which things do we think we have in y equals the absolute value of x on 2 plus 3? We have an a value and we have a c value, right? That's all we have. So what we have is we have the graph y equals the absolute value of a half x plus c. Does that help plus 3, sorry. Does that help people see what our a value is and what our c value is a little bit clearer now? So we need to describe our transformation. So remember, we always start with horizontal dilation. So we have horizontal dilation, where a equals a half and a scale factor or equals 2. So remember how we get our scale factor. Our scale factor is equal to 1 on a with our horizontal dilation. And then we just have our vertical translation. C equals 3 and 3 units up. So what that means is our coordinate x, y. What's going to affect our x? The 2, right? Our scale factor affects our x, so it's going to be 2x. And what's going to affect our y? So it's going to be y plus 3. So what we are going to do is we're going to think about our parent function. So our parent function is y equals the absolute value of x. Now, y equals the absolute value of x has the points 0, 0, 1, 1, 2, 2. We can chuck in a cheeky minus 1 as well if we like. Okay, what we then have is our transformed function. Is y equals the absolute value of x on 2 plus 3. Sorry, my pen's gone weird. So in order to get to our transformed function, it is going to be 2 lots of our 0, 0 plus 3. So that means our transformed point there will be 0, 3. Then with our next one, we have 2 lots of our 1, 1 plus 3. So that becomes 2, 4. Then we have 2 lots of 2. So, and then 2 plus 3. So that becomes the point 4, 5. Oops, I was going to write that in pink, wasn't I? So that becomes the point 4, 5. And then lastly, our 2 lots of minus 1 plus 3 is going to become minus 2, 2. What have I done? So minus 1 is our... Oh, it's minus 1, 1. I stuffed up the point originally, didn't I? Oh. So it's going to become minus 2, 4. I was wondering why it wasn't working out. I was like, what's happened? Okay, so now if we were to sketch this, we are going to go 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, minus 4, and 1, 2, 3, 4, 5. So if we sketch our transformed function, we're going to have 0, 3, we're going to have 2, 4, minus 2, 4, and 4, 5. So we can then draw our nice straight lines between our points. And our one. At minus 4, it's also at 5 because this is a even function. It's symmetrical about our y-axis as well. So that's our y equals our absolute value of x on 2 plus 3.